In the previous lecture, I had shown you this diagram, so please make a correction there. I just said that it will be G sine theta by A, but please make a correction. This pressure will be G cos theta divided by this cross-sectional area. Okay, so we know that pressure is always compressive in nature and always perpendicular to the surface. So for this particular surface A, just G cos theta component is perpendicular, so we can write G cos theta by A is equal to pressure. Okay, so let's proceed further. Stress we defined earlier. What is stress? Stress is defined as the internal resisting force per unit area of the material from which the component is made. You should write a note that stress is not scalar, it's not vector, it's a tensor quantity. What is a tensor quantity? A quantity which needs magnitude, direction and plane for its characterization. So without plane you cannot define stress. When anyone asks you, tell me what is the stress at here, you need to say that at which plane you are asking. Okay, so there is no concept of a stress without plane. So plane representation or plane characterization is important in order to define stress. One more thing, as I told you in the previous class, say we have some external force P which is being applied on this body, and there is some generation of stress inside. There is generation of internal force inside. Okay, so due to this left hand side P, there is a right hand Q. Due to right hand P, there is a left hand Q. Okay, now due to this law, that is the law of transmissibility of force, what does it say? It says that your forces, you can simply transmit the forces along its line of action. So as you can see along this horizontal line, I can transmit this Q force outside, I can transmit this Q force outside. Okay, so this Q which is being shown towards right, I have just shifted it outside. So here I have shifted, and if I take this per unit area, so this I can represent it as sigma, which is called stress. Sigma is called stress. So here, since we are talking about the normal stress, so it's being represented with sigma. Okay, now if we divide this internal force per unit area, which area I'm talking about? This vertical area, that is area A. So this unit or this term is called as stress. This horizontal area B, so I have shown it separately intentionally. If I divide this Q divided by A, so this will not give me the stress at here. So here if we talk about stress, so here I need to divide this internal force with this particular area. So and hence we can represent this sigma as Q by A. Okay, now moving to types of stress. Broadly speaking, we can classify stress under two categories. One is direct stress, one is indirect stress. So direct stress is further classified as normal stress and tangential stress. So this normal stress is represented as sigma and tangential stress is represented as tau. Normal stress can further be classified into tensile stress and compressive stress. So we represent tensile stress as sigma subscript T, and compressive stress is represented as sigma subscript C. So here you can see we have got a 3D body, and in this 3D body, let's consider we have, let's say this is sigma. I'm representing this as sigma x and this as sigma x. So this stress along x-axis, I am representing this sigma y and sigma y. So this is along y-axis. Then this sigma z and sigma z, so this is along z-axis. Okay, so this is the nomenclature provided. You are assuming this axis as x-axis, this as y-axis and this as z-axis, but absolutely it's not mandatory that you have to assume this horizontal only as x-axis. If you want to rotate it, you can assume any of the axis with any of these notations or variables. Alright, similarly for compressive stress, if we talk about, so this we can represent as sigma z, this as sigma x and this as sigma y. Moreover, you should keep in mind that this tensile stress, whenever we talk about tensile stress, we give a sign convention for this as to be positive. So we write the positive values for this, and we give the sign convention for compressive stress as negative. So we write negative values for this. Moving to the another section, which is your tangential stress. So when you shear, when you rub anything, so see here, if you are applying any force, so just opposite of that there will be some shear stress generated. So I have represented it with tau on this top and bottom surface. Okay, so if I want to find tau, I can say this is nothing but the shear force. Let's say the shear force is being applied on this particular surface is P, and this area, if I divide it by B, will it give me this tau? No, this will not give me tau. I need to divide which area? I need to divide with A. This will give me tau. Similarly, if you want to find the shear stress on this vertical planes, then you need to divide the shear force acting on this to that of the area of this particular plane. Here, if you want to talk about, so here let's say sigma is given as P by A, and here sigma is also given as P by A. What is A? A is the area corresponding to that plane which you are talking about. Okay, so the formula for this tensile stress and compressive stress remains same, only the nature changes. That tensile stress comes out to be positive, compressive stress is considered to be negative. We'll talk about this convention of all these some also later, but this just a mild introduction. So here for this bending stress, you should remember one universal bending equation, that is sigma by y, or sigma b by y is equal to m by I equals to E by R. What are these? We will deal this sometime later, but it's suggested that since you are starting your strength of materials, you just mug this relation. Similarly, we have tau by R is equal to T by J is equal to G theta by L. You should have this relation always on your tips for solving the numericals. What are these? You will come to know sometime later, but you should learn these relations here itself. Then we have some indirect stress. So indirect stress is due to bending and torsion. So bending means when you are bending anything, torsion means you are twisting anything. Okay, so when you are bending, there will be compressive stress, tensile stress as well, a combination, and here also we have some shear stress generated due to this torsional or twisting nature, okay, which is called as torsional stress. Now what is the difference between this shear stress and this shear stress? So this shear stress is occurring due to twisting, and here we have shear stress due to rubbing. So that is the only difference. So here this shear stress is occurring due to rubbing. So rubbing is an action. Okay, so due to rubbing, this shear stress is coming into picture, and this is coming due to twisting. So these are the different types of stresses. In the subsequent lectures, we will start picking up one by one and doing the analysis. See you in the next lecture. Till then, bye.